In this video, I'm going to be going through moment couples. So moment couples are a concept. We talk about forces, moment forces. In this video, we're going to talk about moment couples, where we have pairs of forces. Okay, to start off with, the most obvious, I think a really good example that illustrates this point is that if we have a plane, we have here the center of mass, and then here we have the weight, or mass times gravity, mg, and we have the lift that is generated on the wing. Now that looks great. If we have some of the forces vertically, that makes a lot of sense that these two forces balance each other out. The problem is, because there's a distance between these two forces, they're actually going to form an infinite spin if there was nothing else to balance them out. So we could see here we'd get an infinite spin. The plane would be continually turning. So what we need is another force to balance out those forces in order to prevent that infinite spin. In the case of planes, it's just a regular force, but what we're going to look at later is moment forces. So let's talk about the plane first. In the case of the plane, we have the lift generated on the tail. Now, the lift generated on the tail usually acts downwards in order to counteract that spin. So that in this case, we're going to get some of the forces are still equal. Right, these wouldn't have to be exactly the same, because if they were exactly the same, it wouldn't work. The lift is going to be greater than the weight and the downward force on the tail. But when we look at the moments in these equations, let's have a look here. So if we have the moments measured from the center of mass, we know that the moments about any point are zero. But if we're going to, for the sake of our argument, we'll take it through the center of mass. What we have is that the distance to the wing multiplied by the force on the wing, which is going anti-clockwise, so that's a negative force, negative moment, is being counteracted by the lesser lift downwards on the tail multiplied by the distance from the center of the mass to the tail. So those two forces, those two moments will be balanced out. Okay, this is a question. This is an example I took from the Year 12 book. Right, we do this in the third unit in Year 12. It's not something we necessarily need to worry about. I just thought worthwhile seeing where that came from. We work with much simpler examples. So this is from page 61 of the Copeland textbook, where it talks about couples and couple forces, or force couples. So the idea is that when we want to find out the moment couple, that's moment C for couple, we can just take one of the forces, 1F, multiplied by the distance between the two of them, D. So they give an example. It's sometimes easy just to get straight into the examples, is that the moment that is generated when we turn the key on a tractor, right, the key is, it's a big key, 25 millimeters from end to end. So when the driver is turning the key, he or she is applying a force to the top of to the outside edges of the key. And they're applying 10 newtons. We just take one of those 10 newtons. Right, 10 newtons times 25 millimeters gives us, now I would write that as 10 times 25 is 250 newton millimeters, but Copeland likes to do everything in SI units, so instead he has 10 times 0.025, which is 0.25 newton meters. Moments are measured in newton meters. We haven't talked about that up until now. The reason why we haven't talked about moments being measured in newton meters is because we usually divide out the distances, right? So when we divide by the distances to find a force, it doesn't matter if we measure in millimeters or meters, because as long as we're consistent, it's going to be the same. In this case, this is the first time where we're seeing that moments themselves actually have a unit of measurement, and that is newton meters, or newton millimeters, or kilonewton millimeters, or something like that. So typically in Year 12, just a bit of foreshadowing, when we do civil structures next term, we will get answers that will be in kilonewton millimeters, and kilonewtons, and we want to convert them into newton millimeters. I'll talk about that, why we want to do that later, but for the moment, just because they're grease units, but for the moment, let's continue on. Okay, so I have a similar question, and we're just going to look at it here. So you'll notice that when Copeland did it, he just talked about the distance. He just took one force and the distance between them. I just want to prove to you that if you take two forces, it works as well. So in this case here, we have said that the F1, the force, both these two forces are 5 newtons. And we've said that the distance, this is a reasonable tap, is 25 millimeters from this point X. I've labeled the center of the tap as X. So what we have is 25 times 5 plus 25 times 5 equals the reaction, and in this case the reaction force will be a moment. So we get, that should have actually been in Newton millimeters. I think I changed that when I took my photo. I do not care enough to change it, so we're just gonna, I would almost get the paint tool out to adjust that, but have to live with it now. Okay, so the answer is actually Newton millimeters. Units are important, guys. Make sure you get your units right, especially before you set up to record a video. Okay, we're going to continue on. So here we have pretty much the same question, right? We're finding the force couple, right? So I referred to it as a reaction moment, but here a moment couple is a good way of referring to it. And here they've told us that the moment couple, the resistance to turning, right, is a torque of 20 Newton meters. And so what we can say here is if we know it's 20 Newton meters divided by 0.55, because we need to convert that distance to meters, gives us a force on each side of 36.36. Okay. Now, these questions are where we get a bit more interesting. I find these questions are pretty trivial as long as you get the right units. Bad Mr. Punsit, right? But these questions are where it starts to get more interesting. So let's have a look at a bracket. A lot of you will have made a bracket that looked like this in year 8. And so I didn't choose great units here, but we'll live with it. What I've said here is that we're hanging a plant off this bracket, and the plant weighs 2 kilograms, which multiplied by 9.8 meters per second squared, which we're just going to call 10 for the sake of our argument. We have a 20 Newton force being applied down. Okay, so that makes sense. We would assume that our vertical reaction should be 20 newtons, right? That balances the sum of the forces being equal. Sum of all vertical forces means that RV has to equal 20. The problem is that we can see here we get an infinite spin. That's bad. Wouldn't work in reality. Now, the fact is that in order to okay, so I'm setting up the question here. So the reality is that there's a wall here, and that what's going to happen is that if you had this bracket, that this is the point where if this bracket was, let's say it was moving up and down to the wind a lot, where we'd see the bracket actually start to scrape against the wall is here. This is where the force is being applied, right? The force is being applied at that corner, yeah? There's an outward force at this corner that's pushing everything to keep it to keep it balanced. The other place where it's being forced on is, okay, just to explain. So if we know that there has to be a force pushing out from the wall, we can see that with one force, the sum of our forces horizontally aren't equal to 0. They're not balanced. So we need to have another force pulling the bracket back in. So we have one force that's pushing the bracket out at the bottom corner, and we have another force that's pulling the bracket in at the bolt. And this is the bolt that I've drawn here in hidden detail. So here I've got the force on the bolt and the reaction horizontally. And what I want to do is I want to calculate, if I know that this is the 20 newtons, I want to find out what is the distance between these two things. So I want to know what point do I have to put my bolt in order for these to be balanced. It's not a realistic question, because the realistic question would be that the forces would change, not the distance between the bolts. But this is the question I came up with when I was doing it on the board. Okay, so I've said some of the forces vertically is 0, therefore the reaction at V is 20. The sum of the forces horizontally is 0, therefore FB has to equal RH. Okay, so let's have a look at what have we got here. So we continue on and we say that the sum of the moments about... Now, I have done this 3 times to show you that it doesn't matter where you take moments. You can take moments from J, which is the corner, K, which is the middle of the bracket, or L, where the force is being applied. It doesn't matter, right? Whichever one you do, it's going to be the same. But for the moment, we're going to take moments about J. So what have we got? We've got this 20 Newton force, and we've got a 20 Newton force going up here, right? RV. So I've said RV, well, RV is being applied there, right, which is in line with J. I know I drew the arrow there, but in actual fact, the force is actually being applied here, right, which is in line with J. So there's no perpendicular distance for RV. Its perpendicular distance is 0, so we just multiply by 0. Then we have a clockwise moment. This force here is pulling down, it's rotating about J, so it's going to be going clockwise. So clockwise, and I've said the distance from the wall to the center of mass of our plant is 180 millimeters. So our answer here is going to be 3,600 Newton millimeters. Just to demonstrate the same thing no matter where we go, if we're talking about K, right, the force couple that we're generating is going to be here. It's going to be 20 times 90, right? 20 times 90 clockwise plus 20 times 90 clockwise. It's the same thing. Or we can do it here, where if we measure from L, the distance from L to the force being applied up here is 20 times 180 plus 20 times 0 equals 3,600. The point I'm showing here is it doesn't matter where we take moments, it's always the same. Okay, this is just highlighting that detail. Here I'm saying same answer for some of the moments at J, some of the moments about K, some of the moments about L, they're all the same. Okay, so once we know this, we can just say our moment couple equals force times distance, right? Now what we know here is that our force is 20 and the distance between the two forces is 180, so what we proved above is 3,600. Now that we know that this force couple, in order to balance the vertical force couple, we're going to have a horizontal force couple that needs to be balanced out. What we know, that the two force couples have to both equal 3,600. So in this case, this unknown force, FB, or we could use RH, doesn't matter which one, we just have to take one. If we know the two are the same, it doesn't matter which one we use, right? It's the distance times one of the forces. We have FB times 200, so 3,600 divided by 200 equals 180 newtons. That doesn't look right either. That should look like it should be 18 newtons. Again, I made a mistake. I have addressed that. Here we go. I fixed that up. Good work, past Luke, for spotting that I've got an error. And good work, current Luke, for doing estimation. Estimating, I've said before in class, is a really important skill, right? It helps you to spot errors. It's like having someone go and check your answers in the HSC. Yeah, the more I know that it's a time-consuming skill to develop, but it's really important. Okay, so here we've said that FB equals RH. I'm proving here that it doesn't matter if we take the moments about RH, it's the same thing. I did FB above, but if I do RH below, it's the same thing. The only difference is that FB is pulling to the left, where RH is pushing to the right. Okay, Copeland has another question on page 66. Let's go through that one. So Copeland's question on page 66, we have a bracket that is 320 millimeters long to the point where the weight is being applied, and the distance from the point at this bottom corner and the bolt is 80 millimeters. That's the information you need to know. So let's have a look here. We've got our bolts, the distance from the bolt to the corner where the pushing force is going to happen at that bottom corner. Okay, so I've said that it's 10 times 9.8. I said 98. This time I didn't. I did gravity as a more accurate value, right? I guess I was feeling, I don't know. I felt like doing more work for myself. I guess I didn't do a lot of the calculations here. Okay, so what have I got? RB is this force here, but I'm not going to use RB for the moment. For the moment, I'm going to break RB into two components. I'm going to break RB into a vertical component, which is RBV, and a horizontal component, RBH. Now, I've just said that the reaction at this corner is RA, and the reaction at the bolt is RB. Coincidentally, or conveniently, RB is the reaction at the bolt. So let's have a look. We keep going. We have said the reaction vertically at the bolt. Now, keep in mind, even though I've drawn the arrow here, the force is actually applied there. The force is actually being applied in this line. But there's a reason why we separate those lines out, and that's just to make it clearer, so to make it visually easier, even though conceptually it makes it more difficult. So bear with me. See how we have that 320 distance? The force is actually being applied along that line. Now, as we continue on, what are we looking at here? So we're working at the moment couple. Okay, the moment couple, we have one force, 98 newtons, multiplied by 320, gives us our couple force. Now, I did that in millimeters, which gave us 31,360 Newton millimeters, and I've converted that into the units Copeland-likes, the SI units of 31.36. Okay. Therefore, that same couple has to be, that's the same moment couple for the vertical couple has to be balanced out by an equal and opposite force from a horizontal couple. The horizontal couple has the same 31,000 newtons. The distance between them is 80. Therefore, the reaction at RA equals 392. It's also going to be the value of RBH, right? If we know that RBH equals the same thing, RBH equals 39 newtons backwards. Now what we want to do is we actually have to find RB. The actual answer requires us to find RB. So let's have a look. We have this line, and this vector is 98 newtons up and 39 newtons to the left. The value of that is going to be 392 squared plus 82 squared. Take the square root of the whole thing. Happens to equal 400. I didn't check it, but it sounds about right. And I said too, it sounds right because it's a hypotenuse. It has to be bigger than this value here, right? It has to be bigger than 392. In terms of the angle, right, I use the arctan, which in Excel is a tan, or it's tan to the -1, right? That's the button. That's what often the calculator will show that. Excel will say a tan or arctan. Its tan is opposite over adjacent. So we always measure our angles from the horizontal, right? So the angle from the horizontal, the opposite is 98 divided by 39.2. So it's about arctan of about a quarter is 14. 14 degrees, again, I didn't check it, but it looks right. It looks like it's in the ballpark. I mean, I've drawn that at 30 degrees, but it looks like it's a plausible angle, right? Okay. Here we go. Turning off a water valve. Okay, so these are chapter review questions. So these are on page 86 of the Year 11 textbook. It says there's a 100 Newton force on each end, multiplied by 300. So in the case of Copeland, he likes to use meters. That's fine. The answer will be in meters. So we're going to say 100 times 0.3 equals 30 Newton meters. So I haven't looked at the answers, but I think it's a pretty reasonable guess. Here we have a sign for roses, right? What is the force a couple if the sign has a mass of 2 kilograms? Well, it's going to be 2 kilograms, which is 20 newtons. A bit of a trick for people. Some people wouldn't have remembered to multiply by gravity. So 20 newtons times 0.2 meters, right? So 20 newtons times 2 would be 40, so it's going to be 4 Newton meters. Again, too lazy to check. If I got that maths wrong, yeah, I'm not even using a pen, so I don't mind. Okay. Question 25. This one we did do on the board because I thought this one was interesting enough to do on the board. A 10 kilogram mulcher, so we should be thinking straight away 100 newtons, is held in the wall by a single bolt as shown. The center of the gravity is 90 millimeters from the wall. What are the horizontal forces present on the bolt? And they've shown the distance from the place where we're going to have our horizontal reaction and our outward pushing force and our pulling force is going to be 135 millimeters. Okay, so let's have a look. What have I said here? I've said, first of all, what is the value of the... Well, sum of the forces vertically equals 0, therefore it's going to be 100 newtons down and 100 newtons up applied. I've actually drawn the arrow applied properly here at RBV. Then I need to find out the value of the moment couple. The moment couple is 90 millimeters times 100 newtons equals 9,000 Newton millimeters, right? And then that same, if I have a is this a clockwise couple? It is a clockwise couple. If this is a clockwise couple, in order to balance it, I need an anti-clockwise couple applying at the wall, and that's what I have here, an anti-clockwise couple. The anti-clockwise couple is going to have the same value, so it's going to be 9,000 Newton millimeters. The distance between the two forces is 135, therefore both forces will have a value of 67 newtons. RA is 67 newtons pushing out of the wall. RBH is 67 newtons pulling into the wall. Okay, once I've found that, I can say RBH is 67. This is 100. I know that this value has to be bigger than 100 because it's a hypotenuse. I can guess my angles are going to be about 60 degrees. Okay, I use Pythagoras' theorem to determine the answer is 190. Again, my estimation works. I used arctan of 100 divided by 67 gives me 56 degrees. Happy with that. Okay, that is the end of what I want to talk about with couples. I'm irritated a little bit that I got the units wrong on one of the questions. Nobody's perfect. Sorry about that. I'm not even sure I'm going to keep that last little bit in. See ya.